Welcome back to Developers Toolbox. Today we are doing the second in our series of talks on encryption, hacking, hashing, security, etc. So last week we kind of kicked this talk off with a brief history of encryption, and we talked about encryption and where it came from. This week we will be talking about hashing and kind of how hashing differs from encryption and what it's useful for and how it works, and we'll talk a little history about that too. But before we get too deep into hashing, I do want to kind of clarify a point from last week. The real kind of take-home point, the biggest one from last week's conversation about encryption, is that encryption, in order to decrypt a message, you have to have the appropriate key to do so. Probably the most important thing to keep in mind is the security of that key. So, well, there's always hackers sitting in the middle of a conversation trying to decipher your enciphered message. The way that that's most commonly accomplished is through theft of the key that is used to decrypt the message by the legitimate party that should be receiving that information. So protecting that key is of the utmost importance, and this is why, generally speaking, I am dubious about third-party encryption solutions, things where you're not necessarily in control of the key that's being used to orchestrate the encryption, and therefore it really isn't secure because you're putting your trust into some third party to protect that key in the same way that you would. Just purely as an example of that, just column-based encryption inside of SQL Server, you can still use management tools to issue queries against that database, which tells me that key is somewhere where it may be easily exposed. And so a hacker who's compromised my application level database probably also has access to my system level database, can retrieve that key, and my encryption is effectively useless. So that's why I really like to ensure that whatever I'm using, in the case where I need to securely transmit data, I always want to make sure that that key that I'm using is secured, and that I'm in control of it, and that it only gets shared with the people I intend to share it with. So just kind of a takeaway from the encryption talk. Let's go ahead and get into hashing, which is a little bit different than enciphering, which we talked about last time. I did mention hashing last time, but we didn't really go into a whole lot of detail. So let's talk about it. What is hashing? So hashing is a set of cryptographic functions that have some different properties from the type of functions that you would use for enciphering a message that's intended to be deciphered. So hashing maps data of an arbitrary size, which is often called the message, to a fixed size digest or signature. So this means that if my data is this big, then my signature, my digest, is going to be this big. And if my data is this big, you can't see where my arms are, my cryptographic signature or digest is still going to be this big. So it's a fixed length descriptor that uniquely identifies a smaller or larger set of data. It's just a fixed size identification of that data. It is deterministic, meaning that if I use the same hashing function against the same data multiple times, it's always going to produce the same signature or digest result. It is one way. I cannot take a signature or digest and determine the data that was fed into it to produce it. So this is kind of like encryption without decryption. You cannot take a piece of hash data, a hash, and kind of determine what was used to generate that hash without a whole lot of work. And that's the idea behind hashing. It's generally unique. And I say generally, it is theoretically always unique and should be, except that there's an idea of collisions within the context of hashing algorithms. And we'll talk about that in a little bit and what the implications of it are. But generally speaking, when you hash some data, you're going to get a unique result than if you hash different data. You can't hash two pieces of data and get the same fixed size digest. They're always going to be different. So fixed size digest is kind of like an auto incrementing primary key or a GUID or what have you. It's a unique identifier for a piece of data because it is generally unique, and it's just a one-way hash that creates a fixed size digest. Also, another kind of interesting property of hashing algorithms is that small changes to the message, being the data that we are throwing into this algorithm, drastically change the digest, or the output, the fixed-sized output that we're producing. Interesting stuff. Hashing clearly has some unique properties that we don't get with regular encryption algorithms, where we have a key and we can decrypt the data. Hashing is one way. We can't do that. And it's deterministic, which is not a property of enciphering algorithms. We expect to get the same result every time we apply the same hashing algorithm to the same data. It's always going to be the same. So hashing, where did it come from? Let's talk about the history of hashing algorithms. It hasn't. It's not a concept that's been around as long as enciphering has, for example. But in the 80s, we had a series of message digest algorithms, MD1 through MD4, which were used to create a hash of some data or some information. And that was largely perfected in the sense that it could be. That algorithm for message digest was largely perfected in 91. And it was that was the fifth iteration, or MD5. And that was the first of these hashing algorithms that actually appeared in RFC. That was RFC 1321. And so MD5 was considered to be a relatively reasonable way of doing hashing for a long time. In semi-recent history, at least, it was proven that that's not the case. There's too many ways to produce a collision in MD5, or two situations where there's multiple different values that you can feed in and produce the same result, which defeats the purpose of having hash data to begin with. And we'll talk about the application of hashing. But suffice it to say, MD5 is not the way to do hashing in like 99% of situations at this point, just because it is not a secure way of accomplishing what hashing attempts to accomplish, which again, we'll get into applications in a second. But anyway, so then in the mid-90s, there was a capstone project. This was the U.S. government produced a set of standards for encryption and specifically hashing algorithms. And this was originally SHA-0 or SHA-0 in 1993, evolved into SHA-1 in 1995. But this was a significantly more complex set of algorithms than MD5 was, and so it could produce, there was less risk of collisions. It was considered to be more secure. It used the same kind of like length of of the hashed output, and we'll talk about length here in a second. But it was kind of similar to MD5, but more complex in a way that made it more acceptable for its time, or more usable, less prone to collisions and attacks. And there's a number of other protocols, by the way, in the history of hashing that are not in this list. This is just the most common ones that have been used extensively and are in use extensively today. So Whirlpool was a sort of a unique algorithm that came out of a private enterprise. It was actually based on AES, which is one of the, you may recall from our talk last week, that is one of the encryption algorithms. And it always produces data of 512 bits, and that was used to some degree in 2000 for certain things, but was quickly displaced by SHA-2, which was produced by the NSA. SHA-2 was the first of these algorithms that had some interesting properties, where the output length, what was produced out of the algorithm that represented the signature or digest could be variable in length. Up until this point, everything was fixed length, but now you could use a combination of sort of pseudo algorithms underneath SHA-2. You could use 224 and or 256, or you can use 384 and or 512, which the numbers on these indicate the number of bits involved. Although these cipher suites actually do verify or do produce digests in slightly different ways. This was in 2001, and again, this was produced by the NSA. And so for a long time, this was very much the new kind of ideal hashing algorithm. It displaced pretty much everywhere. It displaced MD5, even where SHA-0 and SHA-1 had failed to do so. SHA-2 was pretty much the way to go up until recently. relatively recently in 2015 when SHA-3 came out, which uses a different underlying algorithm and includes support for a couple more different ciphering mechanisms to include SHA-128 and 256. But the output sizes were variable, same as SHA-2 was, and you could produce the same sizes of hashes as you could with SHA-2. And so SHA-3 is now considered to be the standard for hashing algorithms and pretty much what's used across the board. What are hashing algorithms? Why would we use them? Where would we use them? So let's talk about applying hashing algorithms. The first use case that I could come up with for hashing algorithms is file digest. And so this addresses several issues with transmission of files effectively. So there was a time, and this was very popular especially in like the 90s and the early 2000s, where if you produced a large file and made it available over the internet for download, transmission reliability could still be kind of a problem. You may not receive the entire file, and it may not be able to be reconstructed in the exact the exact bytes that it was originally created in. Maybe some little piece of information went wrong somewhere along the way in transmission. Transmission was not entirely reliable, and even still to this day, this can be a factor. But basically, any time that you're moving a file from over here to over here, and you want to make sure that the version that you had originally over here is the same as the version that you have over here, you can create a hash of the data in that file. And because that hash is unique based on the input and is of a fixed length, it's very easy to verify that the file that was on the receiving end is the same file that was created on the transmitting end. So transmission reliability is a thing. It still is a thing. Like let's say that I am the author of a Linux distribution, right? So it's not uncommon to have ISO files, which are like kind of image files that contain an archive of everything that goes into a Linux distribution, and these tend to be pretty sizable. So they can require a significant amount of time and/or bandwidth to download, and so it's kind of important to verify that what you received on your side is what the distribution maker, being me, transmitted. So I will publicly make available a hash or digest of that file and say this is what a hash of this file should look like on your end. And you can just run the same hashing algorithm I did with your file, and if your hash matches mine, then you know that the file you received is the same file I created and that there were no errors in transmission. Of course, this also has the additional effect of tamper-proofing files. So if you're worried that maybe the file that I created is something that you want to use, but somebody messed with it somewhere in the middle, some man in the middle like maybe appended a virus into my Ubuntu distribution that I created. And so you want to make sure that the file that you've received is actually the one that I authored because you received it through a different channel than I distributed through, like maybe it's passed hands several times, and you just want to make sure that nobody's messed with that data. By running it through the algorithm and comparing it against, again, that hash that I made publicly available, my public digest of that same file, you can confirm that the file that you have in hand has not been altered by anyone along the way. The data that's in it is the same as the data that was in it whenever I made it available. So you've got transmission reliability, you've got tamper-proofing, and plus hashing is just quick and easy. It's not hard to actually take a hash of a file. Case in point. Bear with me for 1 second here. Let me find a good file to hash. Let's use my server list. I believe this was from a previous Toolbox talk. Anyway, let's say that this server list is something important that I'm making publicly available, and you're worried that somebody in the middle may have altered this. It's real easy to generate a hash digest of this. I'm using MD5 right here. Again, MD5 has been largely deprecated, but for the sake of what we're doing, it's actually pretty simple. So I can just MD5 sum this file, and this file could be hundreds of megabytes or gigabytes or whatever, and this MD5 function is going to still be fast enough to produce a small digest signature that looks like this. And it's pretty easy to, again, on the receiving side, to run the same algorithm and produce this same result. So there's, quick and easy. I can also do let's do a, sorry, let's actually do a SHA-512 with the same file. And remember we talked about with SHA-3, which is effectively what I'm doing here. It's a combination of SHA, one lower end SHA algorithm, one higher end SHA algorithm. Suffice it to say, same kind of operation here. We have 512 bits represented here for our kind of signature or digest. Let's talk about another place where hashing is really useful, and this is my second and also last example, but it's also the most common one, and that is password security. Why is hashing so good for password security? Why is it used everywhere where we need to secure passwords? Well, let's revisit the attributes of hashing again, shall we? What is it that a hashing algorithm does? Well, it's cryptographic. Means little to nothing here, but sure, sounds great. Cryptographic, password security, yeah, why not? Maps data of an arbitrary size or message to a fixed size digest. Now this is a real tangible benefit when it comes to password security, because I can either have a really short password, which is really bad, or a really long password, which is really good but is large. To put it simply, we can condense down the large passwords and size up the small passwords and have a consistent size of digest that we can store in a password database. So this whole mapping an arbitrary size of data to a fixed size of data is amazing for actually storing a signature or a digest that represents a password without storing the password itself. Deterministic. Whenever we run the same algorithm against the same data, we always get the same result. And this is very, very important for passwords, because the way that we actually do the storing of passwords, we're not storing the password, we're storing a signature or a digest of the password. And moving on to the next point prematurely, one way, we can't take that digest and turn it back into a password, right? And we don't need to. As the owner of the database that is storing user passwords, I should not be privileged to know the passwords of the users who are using that database. It's none of my business, and it shouldn't be. So rather than storing the user password in a form that we can decipher it to double check things, we store it in a form that can't be deciphered. It's one way, and it's deterministic, which means that basically the way that password storage generally works in like 99% of cases. So like this is the way it works with most of the web applications that we work on. So somebody creates a password in some way, and there's various processes and procedures for doing this, but they create their own password. And so when they create that password, it gets passed into a hashing algorithm, predefined algorithm, and it converts that into a digest that then gets stored. Now, whenever that user goes to use their password to log in, we don't try and turn that digest back into a password to compare it to what they're entering in the password field. Instead, we take whatever they plugged into the password field and we run it through the same algorithm. And because it's deterministic, we're expecting to get the same results. So if we run whatever it is that they plugged in through the same algorithm and we get a digest that looks the same as what we stored before, we know that they've entered the same password, with the exception of collisions. So yeah, generally speaking, we don't... rather than storing passwords in a way that we could decrypt them, it is a one-way hash, and we verify that by applying that hash the next time somebody tries to use that password to say, yes, I am who I say I am. Also, with hashes being generally unique, that's obviously a good thing for password security. And with small changes to the message drastically changing the digest, that means that if two different people have passwords that are similar but differ in some small way, their hashes, their fixed size digest is going to look vastly different. So these are all really great properties that really make hashing ideal for password security.